You're listening to Gradient Dissent, a show about making machine learning work in the real world, and I'm your host, Lukas Biewald. This is a conversation with Mike Knoop, who is both an AI researcher and an incredibly successful entrepreneur. He started a company called Zapier about 15 years ago with a very small amount of funding and grew it into a very large business. He then got up to speed on the frontier of AI research and recently started an organization called NDIA, which is one of the new research labs working on the forefront of AI. This is a really interesting conversation. We go into business and how AI fits into business, and then also some of the details on how the new R1 and R10 models work, especially on the AGI prize, which he funded and made popular. I really hope you enjoy this conversation. Why don't we start with R1 and work backwards?
Okay,
so
sounds good.
Let's do it. So R1, obviously this suddenly famous model coming out of China. Do you want to maybe just describe that briefly and then talk about R10 as well and pontificate a little bit?
So these basically two actual models got dropped. R10 and R1, they are very similar in sort of nature to what I would call OpenAI's O1 model. They're these reasoning models, and they were trained in a similar way. We know for sure how R1 and R10 are trained because DeepSeek chose to open source their sort of training methodology for R1 and R10. They really did move the science forward here. I did see a public comment from I think Mark Chen, who leads research at OpenAI on this stuff, that he shared that he thinks that it's similar in spirit to how O1 was trained as well. So I think there's some probably pretty good agreement here between sort of the ideas that have gone into creating both of these systems. And fundamentally, the whole the O series from OpenAI, this R series from DeepSeek are fundamentally a paradigm shift from the type of AI systems that we've seen in the past. For example, from OpenAI, GPT series, from 3 to 3.5 to 4 to 4.0. These are all the same sort of broad paradigm of scaling up pre-training, where we're trying to make these sort of models more intelligent by feeding them, more data, making the models bigger. Now, it is also the case of 4.0 was actually a little this smaller, there's probably some distillation that went into 4 to make it more efficient. But roughly, we're sort of in the broad paradigm of making models smarter by trying to give them more human data, and they're effectively memorizing answers. This means that they really have no ability to adapt to novelty. May have heard of the ARC prize, the ARC-AGI benchmark. What this is it's a benchmark that tries to assert or assess a AI system's ability to solve problems that it hasn't seen before. The data set's highly resistant to just being able to memorize the answers. Even if you're given the training set for ARC, you can't just memorize the training set and solve the test set. This is kind of another underappreciated sort of public point. Legitimately is very hard. That's why it went unbeaten. V1 went unbeaten for sort of 5 years. And in December, we had this big news moment with OpenAI OS 03. They had the 75% score on ARC V1. They had this 85% score with this really expensive high compute performance version of it. And this was showing that this kind of new reasoning type of system has a fundamental new capability that we've not had in computers before, that they have the ability to adapt to novelty. And this actually has some implications in, beyond just that quirky fact. This will actually lead to more sort of robust and reliable AI systems too, which we can touch on. It matters a lot for this agent stuff.
But wait, before we go down that path, we're immediately off track, and I love it. But when you talk about novelty, how do you define that, right? Because I feel there's a lot of debate on are these systems just memorizing or not, and they're obviously not just memorizing text and then regurgitating exactly the same text. I mean, it's quite clear there's some adaptation. There's some form of generalization that comes from compression, right? Because it's not literally a database, right? Which would be a lookup table. Right, exactly. If you had one parameter for every fact, okay, you could just have a database. These GPT style class systems do compression. That is where you get some of the interesting generalization coming from. The sort of claim that I would have is that the amount of generalization they're capable of doing is fixed because the architecture is fixed. Effectively, you've got the transformer underlying architecture in every language model up until last year.
And that means that your sort of level of intelligence is fixed. Yeah, you can memorize more, but the amount of generalization you have, the amount of adaptability you can do from your training data to a new novel situation, it has been fixed, and that has not changed up until O1. O1 was the first prototype we saw last September of a system that actually had a legitimately increased amount of intelligence in its ability to be given a fixed amount of input information, be able to do more things accurately. They're further away from its training data.
But wait, so like, what would you say that, like, for example, AlphaGo couldn't generalize? Like, it seems like in the domain of Go, it could reason pretty well and adapt to novel situations. No, or
it's true for ARC too, right? I mean, ARC's been around for 5 years. There's a lot of state of the art in ARC from a pure solver standpoint. If you sort of disregard the front end LMs, was like something like 50% coming out of the ArcPrice 2024 contest. But they're very, very domain specific solvers. They required researchers to have they basically these systems have all of their G, the G factor, the generality, is being put into the sort of system that solved ARC during the contest that came from the researcher's brain, right? Because the researcher's thinking about the problem. They're trying to model the problem and say, okay, here's what I'm trying to get this computer to do. I'm gonna encode my own understanding of the problem into the system, into the architecture in order to get this thing to work. And it ends up being fairly sort of constrained in domain, and it doesn't generalize well. And this is true for AlphaGo too. We've had AI systems for years and years and years that can be superhuman at humans at games. But the fact has historically remained that, what can you do that these AI systems can't? It's the fact that I could sit you down, Lukas, and teach you a new card game, new board game in a couple hours and get you up to human level proficiency. I could take you into a totally new game. I could go teach you how to drive a car you've never driven before and get you up to proficiency probably in a couple days. This ability to adapt on the fly to a situation or a type of problem that you've never seen before but never trained on is what has been historically very unique and special to you as a human relative to the AI systems that we have today.
And it's probably worth saying, I don't know how ARC is, I think, better looked at than described in words, but
I think we should overlay a puzzle somewhere here.
Totally, yeah, it's for sure to overlay a puzzle. But for someone just listening, I think what's astonishing about ARC is maybe how easy these puzzles seem to be and how these systems do actually fail on these easy looking puzzles. But maybe you could describe a little bit more of what it is.
It looks like an IQ test. It's a grid of colors. It's a 2D grid of colors. We're given some examples of input and outputs. And your goal is to find the rule, to find the pattern between what's the common consistent rule between these inputs and outputs, and then apply it on a test that you're given. And yeah, you're right. It's easier to sort of visually describe or visually see than sort of describe. But ARCs basically challenges you to on the fly recompose knowledge that you've acquired throughout your life, basically on what we call these core knowledge priors. These are things like symmetry and rotation and object detection and tracking and basic understandings of physics. ARC requires you to kind of abstract and compose those core knowledge priors on the fly to a task that you've never seen before. And this is what the sort of historical LM scaling paradigm has never been good at. GPT-4 scored 4%, for example, on the ARC data set, in contrast to the really impressive performance we started to see from these O systems.
Okay, so what changed from 4.0 to these O systems that are doing well? What do they do differently to make it work better?
Yeah, I mean, fundamentally, the strongest thing I can say is from a capability, I can make a very strong capability assertion, and then I can have some informed speculation on how. The capability assertion, you see this in just the score. If you look at ARC-V1, right, for over a 5-year period from when it was first introduced in 2019 up through basically last fall, the best sort of LM, GPT-4 got 4% on it. And then O1 came out, O1 Pro came out, O3 came out, and you saw the score rapidly go from 4% all the way up to 75, 85% on this really extreme high-end performance version of O3. It looks like a straight line, it's pretty nuts. And this is actually a really good thing to see in a benchmark, actually. This means there's more signal in the benchmark, and it truly is doing a capability assertion. It's a little tougher to understand capabilities by looking at these kind of monotonically, smoothly increasing benchmark scores that go slowly over time. When you see something have a sharp bend, you know that something has just distinctly changed. And I think that's the case with these reasoning systems. And specifically, the thing that they have done is they have added the ability to recompose knowledge that they've been trained on in their foundation models at test time. OpenAI calls this like test time compute. This is kind of the broad paradigm of we want to use more test time to, we want to use more compute at test time to like think before we just jump to an answer. You know, GPT-4o, you start spitting out tokens in 500 milliseconds and, you know, that's its answer. Whereas, you know, the intuition here is we want to allow these systems to have more time thinking up front before they have to render a view. And the way they think is by what's called this like chain of thought paradigm. You might have heard like, let's think step by step, right? This like Crom-Tac that came out literally like 3 years ago. This paper actually is very special to me. It was one of the things that got me first into go all in on AI. But this like COT moment that happened in literally January 2022, like we're just sort of like downstream of that moment still. We're trying to figure out how can we apply this paradigm of chain of thought about having the models basically think out loud to themselves in a sequence where you say, okay, hey, what's the next step to solve this problem? Okay, now take the next step. What's the next step? Okay, now what's the next step? And you do this sort of in a big chain, and then the model's able to use that entire sort of chain of thought trajectory to ground its final answer. And this is what O1 does. This is what R1 does. This is what R10 does. There is some differences between R10 and R1 we should talk about that are very important. But roughly,
okay,
this is
before we go there, maybe let's take a moment to be like astonished that this works, right? Because you're saying that these like LLMs are compression algorithms that, you know, kind of can't reason. They can only sort of, you know, do some kind of like limited, you know, generalization. They're now like generating text, and the chain of thought, you know, paper had them generating text in steps. So these kind of dumb models are generating text now in steps, and suddenly you claim they can reason. Like that doesn't seem obvious that would.
I don't think it is, and it's one of the reasons why like I said, I went all in on AI back in 2022. There was this, like up until January 2022, and I co-founded Zapier 15 years ago, been working on it. I was an exec at the time. I was like running all of our product engineering org, like half the company, building our new product stuff. And I saw this, and I'd been paying attention to AI, and I saw this chain of thought paper that came out. And I thought I had a good perspective of like what LLMs could do and couldn't do up to that point. And then this paper dropped where it was like, oh, just by asking them all to think out loud, you saw these performance scores on the reasoning benchmarks at the time were showing really, really large spiking behavior. And they've grown from 30% to like 70% or so. And that was like my kind of like, oh, shoot moment. Are we on track for AGI with this technology, possibly? And I felt that was really important to know, first, just from a Zapier standpoint, like, should we start using this in our products? And also, you know, just from a human, I just want to know, I think this is some of the most important technology in the history of the world. And so I kind of went all in to start understanding the sort of paradigm here. One interesting thing about that old school version of chain of thought, like Zapier was like prototyping with chain of thought in fall 2022 as well, with a very similar paradigm of like ask the model to iteratively prompt it out loud. It has a very low degree of ability to adapt. And we see this even with O1 and R1. You know, the scores on ARC are only about 15%. It is a big step up from the sort of GPT-4o class, you know, the 5% territory, but it's a relatively weak amount of adaptation. The thing that has really made these things work with O1 Pro and O3, and this is getting into informed speculation, is they've added search and sampling on top of the COT generation process. They're not just asking for a single COT and then say, okay, now give me the answer. They are sort of generating multiple COT steps in parallel and saying, okay, which one's the best one? Okay, use that one, now go to the next step. Now ask me for a bunch more, pick the best one, go to the next one. They're effectively doing this like program synthesis or program search at inference time. And this insight has allowed a significantly higher degree of like adaptation is what's getting up to the 75, 85%. And I'll be like, you know, to your original point, this is astonishing. Like it's a big update. I think these systems demand like serious study. And it's also why I'm very excited to see R1 and R10 open source, because I think that's going to allow more people to do the science.
Totally. And before we get into the R1 and R10, what's the human performance on ARC, and where are these best models at today? Like when you say 85%, put that in context of human level performance.
Humans, like smart humans, can get up basically 100% on ARC-V1.
I see.
Yeah, if you like the data we have is like if you take two like let's call STEM graduate humans and put them in front, they'll get 100%. Like I think the actual data we have is like 98, 99% across two. This has been one of the actual flaws of V1 is that we haven't had like strong assertions of human capability. Something we're fixing in V2. We've actually been working on V2 for years now, actually. We put a lot of effort into building it last summer, and we're putting the finishing touches on it right now, and we're going to launch it with ARC Price 2025 this year. One of the things we have with V2 is actually strong human study baseline testing to make confident assertions that every single puzzle in the benchmark is solvable by humans in order to justify the easy for human claim. Because I do think that that is the spiritual guidance of like the ARC benchmark in the future is, I mean, it is true for V1, it will be for V2 and V3 and all future versions, is that we want ARC to represent this concept of things that are easy for humans and hard for AI. And I think that's the gradient we're driving to zero. Because I think if you could get that gap to zero, you legitimately, I think it's gonna be hard for anyone to claim we don't have AGI. If you can't find a single thing that like humans find easy, but computers find hard, you know, I think that's a reasonable like goal to set and a target to shoot for. And this is in contrast to like how a lot of other frontier benchmarks work. You know, Dan Hendryck's like Humanity's Last Exam or Epic AI's Frontier Math. Now they're investing in making like these ever more difficult benchmarks. And I think that's a fine thing to do, by the way. I don't sort of discount that effort at all. I think it's useful. But I think there's something more important to understand from a capability assertion standpoint around like, well, what do humans still find easy? I think that's more revealing of something we're missing in these systems still.
I totally agree, although it's funny. I mean, it's been such a long line in my lifetime, and especially in the last year or two, of like, you know, these benchmarks just being like, okay, this is human level performance. If we get there, we're going to have AGI. And then like over and over and over and over, you know, beating these benchmarks. Like, I guess it's really hard to make this claim with certainty, but do you feel like ARC could be like the last of this genre? Like, is there something else out there that you know, AI solves this, but then there's something left as a benchmark that it can't do that humans can do easily?
What I can say more confidently is that we're going to run the gap of easy for humans, hard for AI to zero. You know, I think that is up to the world to decide, is that AGI? I personally think it is. But that's the design philosophy we have for V2. That's going to be the design philosophy for V3 and future versions. I'll say this, like, V2 is going to look probably pretty similar to V1 in terms of domain because we've been working on it forever. It is harder for computers, but it's still easy for AI. V3 will likely be something that looks very different from what we've done so far. I think it will look like ARC still, but like I think it's going to test different capabilities that humans still find quite easy that the sort of current benchmarks don't. And it will likely also include a sort of formal version of measuring efficiency, which I think is also going to be a really important thing we care about getting up to AGI.
Okay, so R1 and R10, can you describe what those are and how they do, like why they do well on ARC?
So R10, R1, both kind of in the spirit of being trained on COT, chains of thought, and then generating them basically a single COT and then, you know, giving us an answer. I think the really important thing to know about is what differs. Why are there two models? Why is R10 and R1 different, separate? This is a very interesting thing. Like they didn't have to release R10. In my view, R10 is a more important system to understand than R1. And it's for this reason. What does the zero stand for? The zero stands for no human data in the training layer for R10.
Like Alpha Zero, I guess, is homage to that, probably, right?
Yeah, they're training it purely on RL, reinforcement learning.
Right.
They're using domains and math and coding to create verifiers where they can have the model DeepSeek V3 generate a COT, and then they can use a formal domain of like literally just run a computer program and feedback, was that right or wrong?
But just to be clear, before we go down that path, so they're not, obviously there's like an earlier training step where there is human data in it, right? I mean, they can't,
yeah.
I mean, how does it learn language?
There's a foundation model, DeepSeek V3. This is not a forever given though. I think this is going to be an engineering trade-off that AI system developers have to make in the future, which is how much knowledge do we put in the foundation model that we start from, and how much do we have the system sort of, you know, generate itself at like test time, basically at runtime. I think likely what you'll sort of, my sort of expectation is you're going to use these reasoning style systems basically to generate new knowledge and add them back into sort of some like ever-growing corpus of knowledge that they have. And you'll probably use those as your starting points in future training runs and future inference systems that you get. So yes, it is the case. Obviously, 4.0 was trained on human data. DeepSeek V3 was trained on human data. But this is not going to be likely the forever case in terms of the capabilities of these systems. I think you will see, and this is why R10 is important to look at. If it's able to bootstrap itself up in knowledge from literally first principles, like math. Give me the piano arithmetic operators, and I'm going to bootstrap up Calc 3. Like that is something legitimately that a system like R10 could potentially do using RL with no humans in the loop.
Okay, so they train the system they train like a foundation model on human data. And then what's this next step that they're doing with R10, just like specifically? So they're generating chains of thought. And then
it's generating a single chain of thought, step by step, taking the full chain of thought, and then that whole thing is being used to get the final grounding for a final response out from the same DeepSeek V3 model.
And how does the feedback get incorporated? Like,
that
how do
is
they know
done
if it's
offline at training time. So what I just described is kind of like a test time, right? They did inference on how they work, right? It's like, okay, user inputs query, I'm gonna like generate one COT very long and give you a final answer. It's gonna go forward. The feedback loops at training time, this happens offline, right? The developers who did this months ago, where they took the DeepSeek V3 model and had it generate lots of COT, and they had another computer programming looking at all those COTs and giving the sort of training loop feedback of like, was that a good thought or a bad thought? And that RL signal is basically being used to sort of fine tune the ultimate R10 model. And then in the case of R1 full, they actually also allow human experts to label those.
But in the case of the 0, how do they have the model that knows if it's a good thought or a bad thought? Like, how do you cold start that?
This is what's different from 0 versus 01. So 01 uses a grader model, where they have like a neural model basically giving feedback and saying, like in text form, oh, good job, bad job, kind of like style stuff. R1 doesn't do this. It's purely a symbolic verifier, right? So they are like saying, I'm going to take this like, potential code that you've just outputted, try to symbolically run it and use it to give a feedback signal on like, is it good or bad? And that's generally what you're seeing in like this RL space, right? It's like you want to get a sort of final answer, and then you're going to symbolically try to verify that and make a 100% reliable assertion of whether that was right or wrong. Which is you can do it in domains where you can run a computer program to verify, a Python program, a math equation, a piece of code. Does the code compile? Does it get the answer I expect? You've got benchmarks where we have all this stuff set. This is different from some of the 01 stuff where they're actually using a process grader model, which is a separately neural trained one that again, this is all informed speculation. They haven't shared any of this. So this is all like details I'm just like trying to pick up and understand based on these systems. But that's what I understand is they have a separate actual LM model that's giving feedback in their training loop.
So in the case of R10, it's pretty cool they've been so transparent about how they do it. Is it possible that there's domains like computer programs that are really easy to do kind of chain of thought and then verify, but then other domains where it's harder? And so you end up with models that are sort of specializing towards the domains where it's sort of easier to tell if the result is accurate or not?
This is the bet, right? Like, can R10 scale up without having to add humans in the loop? The evidence we have is that O3, which does way better on ARC, like basically effectively beats the V1 data set, required supervised fine tuning from humans to get that to work at a high enough degree of efficiency to make it like tractable. We don't have any evidence yet that you can bootstrap a pure RL-based LM chain of thought system to get there. That's like what you're probably going to see happen though in 2025, I would expect.
I mean, I think another obvious thing that's come up with these models that people have noticed is that they were a lot cheaper to train by orders of magnitude. Why do you have a thought of why that is?
I haven't looked deeply into this. The only commentary I probably can offer here that's interesting is, the ticket price is what people often are comparing here between like what's the commercial pricing rate of like 01 versus what the DeepSeek commercial rate is for their model they're hosting. And because R1 and R10 are open, you can actually run them on your local infrastructure. You don't have to go pay the rate. Like they're giving you basically an at cost. Like it's very close to the actual at cost. And OpenAI's got margin. Their company, they got researchers to feed. They got future research to invest in. Like, they're building a business there. So like my, again, informed speculation is that like there is quite a bit of margin built into O1's inference costs right now in order to fund future R&D. And that the true costs are probably more comparable than most people expect, at least for R1 and R10 versus 01. I think there's this other debate of like, how much did DeepSeek V3 cost to train? Are we hiding the fact that like this headline number of, it cost $5 million to train R1 or R10 obfuscates the fact that there was like a bunch of money that went into training the foundation model. And that is accurate. I have no idea how much the foundation model trained. I haven't looked into this. I have no sense of what it cost. I don't know what a GPT-4 cost either. But I would maybe make the single comment on like from an inference cost. I would sort of broadly put these like our systems and O systems in somewhat of the same bucket from a cost basis, like broadly speaking.
Got it. Okay. All right. Well, thanks for jumping in. I feel like maybe we should take a step backwards. I think, when I first met you, it was like maybe more than a decade ago. You're the founder of a company called Zapier, which I've long admired, but maybe some people have not heard of. You want to talk about what Zapier does?
Yeah, Zapier is an automation company. We try to deliver automation software that's very easy to use for non-technical folks in order to automate largely parts of their business. We're used predominantly by individual people, either in their own life, on small teams, individual teams within large organizations. This is very much easy. It's intended to be very, very easy to use, and that's in contrast with like historically, the sort of automation system that has existed out there. We're used today by I think several 3-4 million businesses in the U.S. We have a pretty large international presence as well from a customer base standpoint. And the core idea is you can connect apps to use. So you've got business software use like Gmail or Slack or Salesforce or whatever. Businesses build internal workflows around these processes. They often have humans that have to like shepherd data between the different steps, make decisions. And this is something Zapier can completely automate for you. And it's easy enough to use for line of business type of folks that you don't have to get an engineer involved.
And I think some of the notable things about Zapier also is, this might be unique. You raised a tiny amount of money from VCs, and then you got off the VC train like almost nobody does, and got to like incredible scale. That's been an amazing return for your initial investors. And I think you're one of the first companies.
We debated even raising the money in the first place.
What's that?
We debated even raising the money in the first place. It was a very practical decision, frankly, to sort of do it. The three founders, me, Brian, Wade, we're all from Midwest. I grew up in St. Louis, and there's no venture capital market in the Midwest really. Maybe there's a little bit, but like 2010, nothing. And so how do you build a business? You build a useful service product, you sell it, you use the proceeds to invest back into the business. And so that was kind of our bias, and how we kind of initially operated. And we went through YC, and we were really debating, should we? We've got this demo day moment. Everyone else is going to raise money. Should we? And we did office hours. Actually, funny enough, with like Sam Altman, who was the guy who we chatted with. They were like, should we raise or not? And I think the question he asked us was like, well, look, what's the constraint on the business? And it was a good question, because I think the legit constraint on the business for Zapier at the time was Brian, Wade, and I were all waking up and doing support until like noon every day. And so it was taking away time to make the product better to not have as much support in the first place. And we're like, oh well, we should go hire a support person. And we didn't have enough cash, on hand yet to go hire that person. So we decided to go, raise a small round in order to be able to hire someone ASAP to give us more product engine time back. And the funny anecdote, sad anecdote, is that by the time we got the round raised, got the money in the bank, found the person we wanted to hire, got them on board, started payroll, and they had their first paycheck, revenue had actually caught up enough to just pay them directly. And so I'm pretty sure you could trace the $1 million that we raised in lineage all the way through to today, which it did allow us to activate though and start, which I think is honestly the biggest value we got out of YC, which was just the activation moment to really go on and go full time on it.
Amazing. And you were also remote first from the beginning, right?
Yeah, another weird thing Zapier did. Yeah, we were a globally remote team and have been since 2011. I think the only other companies at the time that I knew of was WordPress. Automatic was fully remote.
Yeah.
37 Signals. I think those are the only two that we knew about, at least.
And then I think kind of the third interesting thing about Zapier from my perspective is you were very early to use LLMs. I think you were kind of the first company that I saw with real LLM use cases. Can you describe what those were and what that experience is like?
Yeah, I think this comes back to the chain of thought paper that came out in January 2022. Like I said, my background is in engineering, at college. I did mechanical engineering. I did optimization research, which ends up being the exact same math as all this deep learning stuff. I didn't figure this out until 2017, but as soon as I realized
you're on the Gradient Dissent podcast, actually.
Yeah, exactly. Yeah. As soon as I figured this out, I was like, oh, okay. I know how this works. It's like it demystified it a lot. And so I started paying more attention to the research side. But like Zapier was growing, I had other priorities. We had to grow the company, introduce new products, yada, yada. And so I really wasn't like that much paying attention. I read the GPT-2 paper or the release, played with it. I read the GPT-3 paper, gave a whole presentation to the company on it. And, and then it's like, okay, cool. We can do some maybe basic stuff around the margin. Cool tech, but that's it. And then this like January 2022 Chain of Thought, Jason Wu's paper came out. And that's what really got me to say, oh, this might actually be extremely relevant now for what Zapier customers are trying to do. And I actually went to Wade, who's CEO, and I said, Wade, I need you to take back all my half the company. You need to go run product engineering because I need to just go do AI research here at Zapier and figure out what does this mean for us, for our business, for our customers. And so for a good 6-12 months, me and Brian, CTO, just coded all day long and tried to understand what can this tech do, what can it do, what were the limits. And that got us, and this is like summer 2022. So we're still 4 or 5 months before even ChatGPT came out. And we had built tree of thought prototypes. We had built a version of ChatGPT internally using the technology. We had pretty much prototyped all the kind of foundational pieces in probably 3 or 4 months and identified that probably the most obvious place Zapier could start playing first was this concept of tool use. Could we equip LMs that are frozen weights, right, that don't have the ability to take action in the real world? Could we equip them with the tools on Zapier's platform, all the actions, all the search endpoints that we have, and allow them to do more? And that kind of activated us really early on to start building and delivering AI products. And I think that's the reason why we're so early. And it also gave me a pretty, this leads into the later story, but it was also I think what allowed me to start seeing the limitations of this paradigm really early as well, because I talked to hundreds of Zapier customers trying to deploy this AI technology in the middle of their automations to do stuff. And Zapier has been deploying AI agents now for 2 years. So I've just gotten to hear what do people want from this tech? Where does it not work? And the number one problem that they all tell me, and it's consistent across the board, is the promise is there. I get what it can do for my business, but I just don't trust it enough yet to go hands off. And again, Zapier's an automation product. It's different from ChatGPT, right? Where it's you're typing on a keyboard and you get a response, you can audit it. Zapier is running on a server offline. You're not watching, you're not monitoring it. And that was the feedback. I just don't trust it because the reliability is not high enough in how it's operating yet to not put a human sort of in the loop. And this was kind of this feedback was so loud and unchanging from GPT 3.5 to 4 to 4.0. And it was in the same contrast of all this, dogma around scaling hype that was crazy for 2023 into 2024, and just wasn't matching up with my lived reality. And I was like, okay, how the heck do I explain this? I have 2 sets of facts that are incongruent. And that's when I kind of rediscovered Francois's podcast on Lex back during COVID, which is when I think I first listened to him and learned about the ARC benchmark more. I'd actually been thinking about it a little bit, but really dug in and read the On Measure of Intelligence paper that he published in 2019. And that was kind of my aha moment, because I thought that paper did a really good job of articulating the sort of promise of the technology that we've seen and why it's important and impressive, but also where its fundamental limits on just scaling up pre-training memorization we're going to hit to. It was leading to all the facts that I was seeing from customers. And once I got to that conclusion, I was like, well, clearly the ARC benchmark is the #1 most important benchmark in the world. More people should know about it. And going into last summer, at least, it was a relatively obscure benchmark at that point.
And then you made a prize for the benchmark.
Yeah.
Do you want to talk about that?
Yeah,
it seemed
I think the Zapier was where I kind of, in this phase is where you and I, you made the introduction to Francois, which thank you for doing that. I think that's hopefully been a very helpful thing for the world. I think you got hopefully high leverage out of that introduction here.
I got you on the podcast, so that's great.
The world thanks you, Lukas,
right,
for doing that. And yeah, so I'd been maybe surveying research in the Bay Area, at least for a couple, maybe a year, 6 months at that point, on hey, I think this is the most important benchmark. Have you ever heard of it? And the awareness rate on ARC was relatively low. It was 10, 20% of people I met had heard about it. Most of the people who thought they'd heard about it actually had heard about the old bad version from the Allen Institute that had been long beaten by language models. And it was just this, relatively obscure thing. It had Francois and this other sort of Swiss lab, Lab 42, been running the small version of a contest for several years going to that point. So there was some evidence that it was a robust benchmark. It wasn't completely obscure, but certainly in the AI industry, it was the awareness was quite low. And I was like, well, this is direct concrete evidence. It's probably the only major concrete public evidence we have that like there are fundamental limits to pre-scaling. Every other benchmark in the world was like saturating out faster and faster, except for ARC. And I was like, awareness is clearly the problem. And so after your introduction, I flew up to Seattle and I got lunch with them. And I was like, I was pitching them all my ideas of like how to beat ARC. I had some ideas, and it was a fun chat. But I also had some like pretty critical questions of like, well, why do you think awareness is so low? Why aren't you working on it more? And he had really good answers for all the key questions I had. And I walked out of that. I had one question at the very end of my notes when I was flying up that I put together, which is like, pitch ARC prize. And I was like, I was like, okay, I think that it is true that this is just like the reason awareness is low is because it's legitimately hard. Every frontier lab has given it a try. And that increased my confidence. It was a really important benchmark that we should grow awareness around. So I was like, well, one way I know we could probably do that is with a prize. I had just seen Nat Freeman and Dan run the Vesuvius Challenge the previous year, which was super successful at growing awareness around this like kind of obscure problem and growing the status, growing the interest in it to get people to kind of shift gears and work on it. And so I was like, I bet we could do something similar. And that's where ultimately ARC prize came from.
And so what happened when you launched the ARC prize? Was it successful in getting engagement with the, like new engagement with the problem?
I think going into June 2024, again, like 10% of AI researchers had heard about ARC. I think coming out of 2024, the year, like as of December 31st, everyone in tech has probably heard about ARC. So like, I think we solved it. Honestly, my true response is like, I have been continually surprised at how much energy there has been around the benchmark. I'll give you a concrete example of this. We were going into the end of the contest. It was in like early November, and we had a bunch of teams on the leaderboard. One of the requirements for winning the cash prize was that you open source your progress. This is an idea of trying to re-baseline the progress in the community each year. And the number one team, who was it was kind of the runaway winner. They had been on the top of the leaderboard all summer long. Had this like 55% score or something like this. And they emailed us the week before, like 4 or 5 days before the contest ended. Was like, hey guys, we're not sure we want to open source our solution. And I was like, oh man, shoot, is this going to work? Did we get something fundamentally wrong about like how to structure this contest to like help make progress towards AGI go faster? And in the next 72 hours after that call happened, at the close of the contest, there was like two other teams that shot up the leaderboard from like, I don't know, 10th place up to second place. The number 2 team actually was like right at neck and neck with the number 1 team. There was like 3 different papers that got dropped within 24 hours of the contest, that they just timed their ARC research papers to drop kind of like at the same time to like time it and enter the paper contest. And it was just this phenomenal amount of like energy right at the end of the contest that it was kind of just hidden from us. We just didn't see it all. And I think that happened again when OpenAI's O1 model came out. There was just this incredible outpouring of demand for us to test O1 on ARC that I didn't expect. I mean, we had like thousands of people on Twitter like begging us to go test this thing. And so we did, like, and it was really important. I'm glad we did it. But it was just like, there's been these moments of surprise, I guess, for me in terms of its relevancy, and I think how much like awareness we've been able to grow around it.
What kind of insights do you think have come out of wrestling with the prize or with the challenge?
In terms of like structuring contests like this?
No, actually, I mean, in terms of in AI, like, what approaches have worked? Have we learned about how to build intelligent systems? So the classic way that people have been trying to beat ARC for 4 years was with program synthesis, pure program synthesis. The idea is to, you build a domain-specific language. Think about it as like little Python functions, Python transformations. And you build this DSL typically by human, like looking at the puzzles and trying to make sort of guesses about what the transformations could be. And then you have a brute force search effectively over the space of all possible combinations of those transforms to look for ones that match your input and output, and then you apply them on the test. This has been kind of the classic way that people have tried to beat it up till, this year, basically. And it doesn't really work well. It's just very slow. It's very inefficient. But and it's very brittle, right? Because it's like all the sort of, generalities built into the DSL that the human is sort of going after. And ARC Race 2024, there was a couple brand new approaches
that were really interesting to see that I think the sort of conscious popularized. I think the first major one was early on about using, it's like an induction-based approach where you're trying to generate lots and lots of like Python programs using language models, and then searching over and like kind of hinting and sort of informing the language model and how they generate a Python program based on sort of the input from the puzzle in order to kind of guide the language model program generation. This is like Ryan Greenblatt's thing. He got a really, really early score, like around 40% or so, using a technique like this. It was very inefficient. Like you need to generate hundreds of millions of Python programs to do it, but it kind of like showed some promise of this like program induction style method.
How do you then pick among, like you generate all those programs, but how do you pick which one looks promising?
You run them.
But
it's RL, right? It's like it's symbolically verified.
When you
generate a program, you can run the program.
But then how do you evaluate if is it easier to evaluate if an answer is right than generate?
Yeah, the data set has the answer, and so it's like, and this is like true of all, math coding. This is like where O1, R1, O3 all really dominate, right? Is in these sort of easy to verify domains where you have an answer and you can check it quickly. If a computer can check the answer quickly and with strong, with exacting correctness, then these types of things will work. And the other big one was test time training. This is the other really big kind of novel approach that we saw come out where, both these basically are trying to adapt to novelty. It's like what they're trying to get at. And the way test time training kind of works is the ARC data set has a public data set and there's a private data set. And this is the one the Kaggle contest, the actual money prize is attached to. It's a private data set no one has seen, or very few humans have ever seen in the world. And you're not allowed to see it when your test gets in order to have strong guarantees around ability to adapt. We're trying to reduce the chance of like cheating or overfitting on the private data set. And so what people figured out is that they can take the private data set inside Kaggle and use that data as a starting spot to generate lots and lots of similar data using data augmentation. They might like change the colors, mirror the grid, things that don't change the semantic rule, but things that generate lots of like nearby permutations. They then fine tune a model using these like, several thousand, tens of thousands of like, locally trained things, and then they inference it. And that actually was working. I think that's what got one of the top 50% scores, was this paradigm of test time training. And I do think that like, you've kind of got two really broad points of evidence now, even with O3 beating ARC-V1, two broad sets of ways that we know about how to use language models to adapt to novelty. One is COT search, which is like what O1 Pro and O3 do. They're doing lots of sampling, lots of search in their per COT step. And then you've got this test time training paradigm where you want to take the situation and try to create data augmentation around that in order to feed that back into the manifold and do inference on it. This is a form of knowledge recomposition, I guess, is a way to think about it. And ARC shows that both these approaches are pretty promising in terms of getting computers to not just strictly memorize what they've been working on before or trained on before.
Do you think if like ARC was broader and not just sort of in this domain of sort of like pixels and changing colors, if that would kind of break that approach? Like it seems like you have sort of contained the domain of ARC by just the format of it. Like I remember reading years ago.
Ways God.
Or I remember reading Douglas Hofstadter book as a kid, I think, where he like makes these sequences of numbers and you just try to like guess what the next number would be in the sequence. Like that sort of seems like a variant of like an ARC-like reasoning challenge, but in a different structure.
Yeah. This is something that's underappreciated about ARC, I think, or a common misconception about ARC is that it is a visual benchmark. I get why this misconception exists, because like we render it visually for humans to take. So the intuition is like, our intelligence systems aren't good at ARC because they just aren't like good at dealing with visual domains yet. ARC should more be thought of as a program synthesis benchmark than it is thought of as a visual benchmark. And the intuition here is that like classic program synthesis is exactly what you just said. It is given a sequence of integers in and a sequence out, figure out what's the rule. How do you map the 1D line of numbers into another sequence of 1D array of numbers? ARC extends that into 2D for the first data set. It's just like, it's a matrix instead of an array. But it's still at its heart it's a program synthesis like challenge of like, okay, given a matrix of numbers now instead of a vector of numbers, what's the transformation rule? The exact same problem statement still surrounds. And now to your, I think to your kind of maybe curiosity here is like, isn't this kind of like domain like constrained? Could you get into like non-formal domains with this kind of stuff? I think this is where like pure program synthesis is not going to be able to do that. You are going to have to, in order to like kind of solve ARC the hard way and build a system that has a lot of domain generality, you're going to need to merge deep learning and program synthesis together into the system. Otherwise, pure PS is just going to be sort of too, I think, fundamentally brittle in order to like represent everything there. You're going to need some degree of being able to like create model descriptions and be a bit fuzzier on the edges around how to sort of capture that model. But ultimately, yeah, I think ARC is today at least a better articulated, at least V1 as a program synthesis benchmark that we haven't made progress on.
Okay, so that makes me think of a question, which is the 2D nature of ARC like essential to it at all?
I think it's an important design principle because it's trying to make us, I think one of the magic, this is all credit to Francois. One of the beautiful things about ARC is its ability to capture your curiosity as a human, right? You look at the puzzles, and I've given them to a lot of people, my friends and family and everyone. You look at the puzzles, and based on all the hype you hear about AI and all coming in last year, and all of the sort of even individual intuition of working with these systems, you look at them, you're like, you take the puzzle, you're like, oh, okay, that was pretty easy. And then you're told, like, yeah, I can't do that yet. And you're like, wait, what? Like, are you sure? Like, what if I just like pasted it? Like, I'll just take a screenshot and throw it to you. Are you really?
Totally.
It just like invites this curiosity moment of like, what's going on here? And that I think is I think it's really standout thing. And why we render the benchmark visually is to like make a strong, not just a claim about something that like is intellectually interesting about, capability we don't have yet, but its goal is to inspire people to work on it. Benchmarks aren't useful if no one actually cares about them. And I think ARC has done a really good job, Francois did a really good job from the design standpoint of making it something that captures your imagination, makes you ask why, and it pulls you down in the funnel of like, all right, let me just try, I have some ideas, let me just go try it. And its goal is to inspire folks, right? Like, this is the whole point of launching ARC-Prize was, we launched it to raise awareness on this important unbeaten benchmark and raise awareness of this like definition of AGI, this design principle we have around the benchmark, and to inspire more AI researchers to go try new ideas. My sort of macro philosophy at this point in my life is basically AGI is the most important technology in the history of humanity. We should be doing everything possible. Anyone who has any unique idea of how to go beat this thing should be to create AGI should be trying to do it, myself included. And this is like I just got really frustrated around how much when I met researchers, talk with venture investors, like how much funding, energy, mind share just going into this one paradigm. And like, even if it's the right one, the world deserves like a few counter bets just to make sure to increase our overall chance that we're going to get there. And so I stand by that. I think we want the strongest global innovation environment we can get in order to get to AGI as quickly as possible, so we can live in that future and use it to actually accelerate the future that like we all want. Okay,
so your new organization, is the idea that you're going to make some counter bets?
Yeah. So Ndea. So Francois and I, we launched it a few weeks ago, officially announced it. Francois and I started to do, I'll call it like a intelligent science lab, basically. And our view is that the way to get to AGI, that it removes most of the bottlenecks that we currently see, even from systems like O3, is a combination of deep learning and program synthesis. We've actually been talking about this for since we started launching ARC-Prize. Like we went on this big university tour and sort of espoused this viewpoint. So you can go find those talks if you're curious to get the gist of the idea. But this is basically the idea. We want to, deep learning and program synthesis are two completely different paradigms. And program synthesis, by the way, program search, is what's making O3 work. So I think we have very strong evidence now that this is the new paradigm that is actually unlocking this new set of capabilities. And my belief is that I think in retrospect, we're going to look at this O3 kind of beating ARC-V1 in December moment as the sort of starting point of another 5 to 10 year scaling journey on program synthesis. In a similar way that we look back in 2012 at AlexNet beating the ImageNet contest. Funny enough, it was literally a contest they're running. And that's kind of viewed as one of the shotgun kickoff moments of deep learning. And I think we're kind of at that point today where we're looking ahead at the next 5 to 10 years. And, what don't we have yet? Like, we don't have, and this is sort of colorful rhetoric, but like, we don't have the transformer for program synthesis yet. There's a lot of technology that has not been invented. If you even just look at the fields here, you've got like probably 1 million deep learning experts now in the world today, or at least engineers in the world today. You've probably got in comparison like a few hundred folks on the program synthesis side. And if this is truly the path to AGI, we're going to need to grow that field. We're right at the starting spot. And that's our basic view, is that we're going to need to merge these two paradigms in order to get extremely efficient AGI technology that doesn't have human bottlenecks in our terms of its learning process.
Okay, so what is program synthesis?
The best way I can articulate program synthesis is probably by example. So it's actually in a really old field. It's older than deep learning is. It goes back to 70s, 80s, and 90s and that stuff. And classic program synthesis is dealing with trying to figure out a program that maps a sort of integer sequence of numbers to another integer sequence of numbers. This is typically the benchmark that researchers have cared a lot. There's even this really cool thing called the online database of integer sequences. It's literally researchers have made hundreds of thousands of these sequences that you can use for this kind of research. And you're given an input sequence and output sequence, and your goal as an engineer is to create a computer program that can automatically figure out what that sequence is. You might be surprised to learn, this is actually a very hard challenge. And the reason is because, depending on the complexity of the program and how much hidden state there is, how many hidden variables there are, programs can be quite long or quite complex. And the longer the program gets, you get into this problem of trying to basically enumerate. This is kind of how people classically try to do it, is they try to brute force it. They try to just search over every possible program that could potentially exist, and they just check it. They're let me plug in the input and see if I get the output. It's extremely inefficient. It's exponential. It's scaling. It's O of x to the n. It's nuts. It's just you're never really going to be able to make this work in a reasonable amount of time. But that's the rough form of the problem, I'll say, is that you're trying to create programs. And I'll map this into O3 because I think how O1 and O3 work, because you can actually use these systems, or at least you can in O1. You can kind of get a better feel for it. With these chains of thought, right? Oh, I give O1 a question. It thinks for a while. It builds a big chain of thought, and then it gives you an answer. A way to think about that chain of thought is like a program. It's a natural language program, but it is a program. It's got individual steps, and each step is kind of like a transformation of the latent space from the thought before it to the step after it. And you're constructing it. You're sort of constructing this program. And what O1 Pro and O3 do is actually program recombination, where they actually search over the space of all possible programs, very similar to how classic program synthesis research, where you're trying to enumerate through options to sort of find it. Again, the big challenge with program synthesis is, and if I contrast deep learning and PS, is that program synthesis can learn out of distribution, or you can find programs that generalize out of distribution. This is in contrast to deep learning, which cannot, right? Deep learning is a paradigm where you need to give it a lot of data embedded on a high-dimensional manifold, and you can make quick proximate judgment calls, intuitions, for inferencing new data off that manifold. But they're not going to be exact. There's no guarantees of exactness, and you need a lot of data. And you're going to get in-distribution accuracy. Program synthesis, you're looking for a program, you only need probably a couple examples. You don't need 1 million. You don't need 100,000. You need 3 in order to find the rule contours of a program that does that. And once you find the rule and you have the program, it's going to work for any input, no matter what input you give it. So it requires very little data. It generalizes out of domain, but combinatorial explosion is your problem. You just can't. It's just intractable to search for all possible programs there. Or in O1's case, search for all possible reasoning chains. So how do you do this? Well, the insight is to use the sort of pros and cons for both sides to merge them together. You want to use, the upside of deep learning, which is to make quick approximate sketches, to inform a search process in order to make sure the search process is not just brute forced. You don't want to brute force it. That's not how humans work. Humans don't sit here and think through every 1,000 Python programs to solve an ARC puzzle. We use our intuition to generate, to do the sort of sketch of a couple possible answers to a solving puzzle. And then we symbolically in our head verify it. We run through the steps. We say, okay, is this right? Is this right? Is this right? And if it's not, well, we go back to our deep learning part of our brain and say, okay, give me some more ideas. And there's a smooth back and forth between the two systems. And we think that's sort of the fundamental substrate here that we can construct around.
It's funny, my co-founder Sean has been doing a lot of work on SWE bench. He recently got the highest score there, and it's a Yeah, it's funny. He talks a lot about the same stuff you're saying. Like, I think, it's a very different domain, but he's using, O3 and O1 to generate programs and then run them and then try to figure out like which is the best one. I guess the runtimes are expensive here, but
efficiency is going to be a big factor. I think this is something the field of AI research has not reckoned with fully yet. When we launched the O3 news, we had to report that on a 2D graph where the x-axis was effectively like token cost or like cost per task, because we're getting in this paradigm now in AI where you can spend more money to get higher accuracy and higher reliability. Now it's still on a logarithmic curve, so it's not like it just it's linearly up here, but like you can spend more money to get a better answer in a lot of domains. And this means that you can't report a single benchmark number anymore. In fact, ARC, we still need to fix this for ARC for next year. Like we need to have our leaderboard with like kind of an efficiency dimension in it somehow. Because like you can't just say, oh, well, okay, that system got 75% on the benchmark. Well, okay, well, how long did it take them to get that? How much did it cost them to get that? These are types of questions I think we're gonna have to like be able to answer and make assertions around in order to inspire and guide research attention to continue to drive efficiency, because I think that's like there's a couple of human bottlenecks remaining in these types of reasoning systems. Once we get past those, efficiency is really going to be the main key thing we have to figure out.
Although if you can, use compute to get better answers, compute cost reliably goes down, right? So the shape of that curve really matters too, doesn't it?
I'm not sure I follow.
Sorry, if you can the slope, even in log scale, of the trade-off between like cost and performance, I think also really matters. Like I would love to spend more money to get better answers in lots of domains.
Yeah, there is definitely a lot out there. One of the major ones that's going to start working this year is agents. Coming back to the Zapier anecdote, the number one blocker for deploying automation with agents right now is reliability. Trust isn't high enough. This is an underappreciated point that I don't think most people have figured out quite yet, is that what does increasing what does the ability to adapt to novelty actually mean in practice? Like, oh, sure, it's a cute benchmark, it beats that. What it really means in practice is you can more consistently get the same answer, not even necessarily the right answer, just more consistently get to an answer from these systems. And that now gives humans the ability to steer them and control their behavior more precisely than we had before. This is going to raise the reliability bar. And I think a lot of use cases where people want to use agents, and it was not a cost problem, it was just like, they just don't work good enough. I'm willing to pay up to human labor rate for this system to work. Now we'll start having those use cases get unlocked as a result of plugging things like O1, O1 Pro, 3, R1 into some of the planning steps for how these agent systems work.
I guess one of the things that's been in the back of my head as I do this interview with you is we're sort of taking for granted that, this kind of like reasoning is important. And I kind of wonder if we're like losing people by showing these sort of toy-like problems in the sense of like, what does that actually translate to in the real world?
Yeah.
You kind of said it, but I guess, do you have an intuition? Where does like the ARC price
failure
show up?
Can I give you a concrete example?
Perfect.
I'll show you
fantastic.
I'll give you a funny story, which is what kind of led me down a lot of this like AI benchmarking path a couple of years ago. When we were first building some of our AI agents at Zapier, we had one that I had set up. Zapier has been a long time strong partner with OpenAI. I've been a part of 3 now, like major OpenAI launches. It's been sort of fun. So we both of us use Slack. We have a shared Slack channel. And when we were building some of our early AI agent prototypes, we had built a system where we wanted the AI agent to automatically send a message into Slack from some lead management stuff coming in from HubSpot, or maybe like our sales team was doing transcriptions and feeding into this process. And when we were testing it, we said, hey, let's have the agent, it's got 2 main functions it needs to fill in to do this automation. It needs to pick a Slack channel to send the customer information to, and it needs to send write the message to the body of the Slack message. And we had the agent guessing both from the inbound message. And our system allowed us to and this is how Zapier works. So you can give hints to the agents on how to fill in those 2 fields. Like you could say, for the Slack channel, I'll use the #testing channel. And this is a plain text description. And for the message, grab the lead, first name, last name, phone number, email, likelihood to buy, and build a lead little widget and put it in. That'll be the body of the message. And when we first turned it on, we had a Slack channel called #testing. the name of the channel we had with OpenAI was called like OpenAI dash like partner dash testing. And the agent just like picked a couple times that partnership channel to like start sending, like information to. And it was like, oh, shoot, that's not good. This is like a production system. It's an important partnership. We don't want it, and like, we don't want customer information being like shared like that.
Totally.
So immediately turned it off, scrubbed it, fixed the situation. But it was my first realization moment that like, oh, reliability and overrides and control are going to be extremely important things for building trust. Because like the first time you see that, you're like, and it's like it's a user who saw that. It's like, nope, turn this thing off. I'm like, get that thing 10 feet away from me. I can't do with this. This is, it's putting my business in jeopardy. And it was very real. It made us realize early on that in order to start deploying AI agents, like a year and a half ago when we started, we needed to offer users hard-coded control over constraining guessing. So in this new case, when you use Zapier's AI agents, you can allow it to guess if you want to, but the default is just choose a channel. And that allows you to have some amount of certainty and guarantees around, well, okay, it's not going to go off the rails too much. Or you can say, here's the 3 channels I want you to guess from. And it allows you to build in that sort of hard guarantee. Again, all this was just early insight that like reliability matters a ton. It's probably the #1 thing that matters for deploying agents that can automate tasks that businesses and users care about. And that is the type of thing we will now start to see get reliably solved using O1, O1, 3. You're not going to see this sort of as much stochastic randomness in doing the wrong thing. If you like build an agent and say, send it to the testing channel and it works the first 3 times, you're going to expect it's going to keep working, and that's going to be the truth. Whereas in the past, with the sort of very, stochastic nature of how these LM pure systems have worked, you really couldn't make that same guarantee without like, some extra guardrails on top that developers created.
And so why did you start Ndea as its own organization versus work with OpenAI if you have this close relationship with them? Like, why do you feel like it needed a new organization?
I think the reality is that if you look at the sort of frontier of what most of these companies are working on, I don't think they share the view that we do about the importance of program synthesis. I spent a lot of time talking to folks, Frontier Labs, OpenAI included, and even showing them, like, you got these over 3 results now. And I think there is a view that we're still in a deep learning paradigm. This is deep learning with a little bit of special search stuff on top, but that's not really that important. I do think there are people, by the way, in these orgs that get it. But I think the broad view still in industry today is that like, deep learning is still scaling. And we fundamentally disagree with that perspective. My view is that program synthesis is at least 50% of the equation. Maybe not from a compute budget standpoint, but from like, if you were to measure like where are the ideas in the future highly efficient no human bottleneck AGI system, it's gonna be half of that is gonna be coming out of the discipline of like program synthesis in some way. And like I said before, I think AGI is such an important technology. Anyone who has like a unique differentiated idea, I think should be trying it. I think it's important for the world. Like, this is why we launched ARC-Prize. We want to inspire more people just to like go try new stuff again, try to get back to the AI industry research model we had in 2018, 2019, where everyone was trying new and different ideas. And I do think ARC-Prize has helped shift the Overton window from a narrative standpoint. I'm starting to see it now. I'm very excited. We're starting to see more fundamental innovation now coming out of a lot of the like small startups. In fact, one of the biggest things that surprised me about ARC-Prize, I sort of expected that we were going to get a lot of individual researchers and maybe some big lab attention to like work on the benchmark. The biggest surprise I probably had coming out was about 7 or 8 startups came up to me some point throughout the contest or afterwards and told us that they had changed these are like AI companies. They had pivoted. They changed the research roadmap to go work on ARC. And I thought that was a really exciting thing to hear, because I was like, okay, I think it's starting to have the impact that we hoped it would, which is to get people to at least explore more and increase the sort of overall probability that like we figure this thing out. And I think we've got exciting long-term ambitions about what we want to use with the technology that I think also differ quite a bit from any of the other sort of major players and companies that exist out there. But purely, if you're just looking at the technology of like, why did we start Ndea? I think it is the fact that we just had I think we have a differentiated view that I think has a high degree of chance of success that increases the sort of probability of getting to AGI quickly for the world. And we're going to put our full effort and attention into trying to make it happen.
And are you also oriented towards making a product and making money and things like that?
I have somewhat an interesting view here. So to answer your quick question, like, no, this is a research lab. Like, we are, like, there's no off-ramp for products in the near term. We're like, this is get to AGI by my definition, our definition, reduce this gap to zero between easy for computers, easy for humans, hard for computers. You shouldn't expect to see us really make products ahead of that. Now, we may start using some of the prototypes of the technology to start trying to advance some of the frontiers of science. This is actually one of the reasons I mentioned, besides just building AGI is step one for us. The thing that gets us really excited, is to start leveraging the technology to accelerate the sort of pace of innovation we see at the frontier of a lot of different fields of science. Like, AGI is going to solve a lot of problems. No doubt about it. It's already solving problems for Zapier customers. Like, it's going to, and it's not even AGI yet. Like, we're like, people are going to use this technology to solve a lot of problems. And that's great. I'm fully supportive of that. The thing that gets me like more excited about the technology is it's sort of like accelerating into this like unknown future. And I'll make this like kind of illustrative story, around like the printing press, back in the 1400s when it was first introduced. Was it 600 years ago now? Like, what was the reaction? It's like, obviously lots of fear and skepticism, but also a lot of excitement around sort of this knowledge proliferation of sharing knowledge globally, being able to exchange freely ideas. I think if you went to anyone though and like asked them, hey, make some predictions about what the year 2025 looks like, you'd probably be pretty hard pressed to get anyone to imagine a future of like Wikipedia and AI that got trained on Wikipedia and like I can talk to computers. What's a computer? Like, we're just so far down the technology like tree from these genesis moments of like that catalyzed everything. And I think that's what really gets me. It's almost more like an adventure than it is problem solving motivated. There's going to be really exciting, cool things that come in the future of technology that I can't even tell you what they are yet. But I think in order to get there faster, the main constraint is like, we need computers that can work in autonomous ways to do innovation. And that is bottlenecked on creating AGI. And that's what I'm really excited to sort of help be a part of and help accelerate if we can.
Do you have a point of view on timeline for AGI?
To the definition I shared before, of like, you've gotten rid of all the gaps from easy for computers, hard for AI. One other thing I think it's actually added to that definition that is worth considering is the efficiency. I think we'll probably reach that definition before we reach it at a human efficiency level. Would be a guess. So let me go ahead and just like add a little asterisk on the end and say like, we're able to sort of, there's no remaining tasks that are easy for humans, hard for AI, and like we're doing it at human level efficiency.
Well, can you put a dollar in human level efficiency? Is that like your salary?
This is literally something we're debating right now, how to measure efficiency. And I don't think the industry knows it. ARC is still, like ARC Prize, we're trying to figure this out too. You kind of want something that you can contrast between humans and computers. And like flops aren't really great. You could maybe do dollars because you could like pay a computer to do X work for X dollars. You could pay a human to do X work for X dollars. Time is kind of interesting from a wall clock perspective because you can make time faster with computers by parallelizing, and that's something they're good at, right? So honestly, I don't know the answer. I probably make the advocation that dollars are probably the best one today based on what I know in order to make sort of comparisons, because dollars kind of, everything fits into dollars, how much you pay a human for labor rate versus how much compute costs. Dollars will track the price performance of compute getting more efficient as well, which is kind of nice. We don't know. So let's say like, human level efficiency, we're paying humans the same we're paying computers to do these like easy tasks that humans find harder. Something like that. I'll add that sort of asterisk on. My expectation right now, if I just had to make some wild guesses, we got ARC-V2 we're working on for this year. I expect it probably will be durable for, let's call it 12 to 18 months. That's my best guess today, based on how it's doing on all the frontier systems that we've been testing it on. It's not going to be another 5-year benchmark though, like the V1 was, because ARC-V2 is kind of in the same domain. It's just like, it's raising the bar of difficulty for computers without raising the bar of difficulty for humans. And this should be an interesting capability. I think it will still be interesting. I think it will still be a good gradient, a tool that will point research in an interesting direction. But the thing I'm really excited about is this V3 that we started designing and kind of prototyping for next year. And our design goal for V3 is that it would be durable for 3 years. That's our hope and goal. We'll have to see, obviously, make contact with reality and all that stuff. But my sort of anticipation is like we will not have easy for humans, hard for AI solved at that level of efficiency based on today for the next at least 3 to 4 years. Honestly, I'll say this: one of the hardest things about making predictions is it's very easy to make predictions around smooth scaling curves. It's extremely hard to make predictions around step function changes in capability because obviously curves you can sort of track out, right? Make future guesses around. Capability disjoints, like if you were looking at the ARC, if you were trying to make progress on when is ARC-V1 going to reach 85% from a general purpose system, it's like going for 5 years, it went from 0 to 4%. And then in 2 months, it went from 4% to 85. That is an extremely hard thing to predict because two things about this. One, you don't know if the technology exists in the world to do it yet. You don't know if the ideas are in the world yet to do it yet. And then if they are in the world, you just don't know if someone hasn't put them together into a system to demonstrate it to you. So you have a lot of unknown variables in trying to make guesses about when do these step function capability jumps sort of happen. I'm not I guess to make my concrete views, I do not believe we're in a pure sort of scaling regime where you can make a nice smooth curve over these system sizes and cast a waypoint out into the future and say, we're gonna have all this stuff solved, we'll have AGI by that point. I treat it a lot more empirically. And I think, you can make informed guesses about when you think step functions might happen, but I think it's in the public's interest to understand that this is actually the reality. We're still looking for step function capability leaps and we don't know when those are gonna show up.
Well, awesome. I think that's a good stopping point for this interview. Is there anything?
You got through a lot of content.
A lot of content, a lot of wide-ranging content. Thanks so much for listening to this episode of Gradient Dissent. Please stay tuned for future episodes.